right, good afternoon. So, final class of discrete structures. And let me set up microphones here. All right, cool. Yeah, thanks. So I decided to dress up for the last day because, you know, normally I dress up every day when I teach in person. And, you know, now that we're at home, I'm lucky if I, like, run a brush through my hair. So I thought I'd dress up to celebrate the last day and completion of fall quarter and the excellent work that everyone has done throughout the term. So, yeah, let's see. Had a question from someone on number of questions on the final exam. So I think it's going to be I think I'm going with 8 questions. And they will, you know, we'll go through the study guide that I posted on Canvas. But, you know, they'll be similar to the homework questions you've been doing all quarter. So, you know, testing your understanding of some concept, writing up solutions to problems, doing proofs, things like that. I may have one of those 8 questions being like, you know, I don't know, 5 short answer, multiple choice, matching, something like that. But, you know, ballpark 8 homework type questions. You have an hour and 50 minutes to do the exam. I don't think it will take the full hour and 50 minutes, but you have, you know, that time available to use. All right, so an hour and 50 minutes. So basically 2 hours. I'll leave Canvas open for 2 hours, but plan on an hour and 50. And then if you need 10 minutes to submit because your machine rebooted or something like that, won't be any panic there. All right, and it will be similar to the midterm. It will be a Canvas quiz. There's a placeholder on Canvas right now that will be replaced by the actual quiz, which will look like a Canvas quiz. And your exam is Monday, 12 o'clock to 1:50. All right. It's not, you know, an open exam that you can take anytime you want on Monday. It's only available between 12 o'clock and 1:50. All right, so make sure you don't miss the exam, because that would be a bummer. Better than 40 physics questions in an hour and 50 minutes. Depends what the questions are, but yeah. I think everybody will be able to do really well on this exam, right? I'm not throwing any tricks in here. I'm not trying to trip anybody up. It's going to be the same stuff you've been doing on homework. Two caveats are, one, you know, I have not graded every single homework question, but we've talked about that. So if there was a question that, you know, you had no idea if you did it right or not on the homework, make sure you ask about it, right? Preferably today, right now, you know, or office hours at 2 o'clock. The other caveat is, you know, we did not have you turn in, and I did not grade your homework for the last unit, which was on languages and grammars. So again, if there's any questions in there you're not sure about, definitely ask questions. Well, you know, if it takes you 10 minutes to do a problem, that's only 80 minutes. You'd still have, you know, plenty of wiggle room left for other things. So mathematical induction, don't be scared of mathematical induction. It's your friend. It makes your life better. Just remember, you know, be very detailed in your proofs, right? Don't figure out how to do the proof, right? But then don't just write down what's in your head. structure it as a formal proof. So how do we do a mathematical induction proof? First, you have to say what you're trying to prove. Prove that, the sum from 1 to n is n times n minus 1 over 2 for all n bigger than or equal to 1. Phrase it as a statement about a proposition. Let P of n be the proposition, blah, right? Prove P of n for all n bigger than or equal to 1. Go ahead and write that out on your proof. And then, say base case, prove P of 1. And usually that's just showing what P of 1 states and then, observing that that's true. And then, say inductive step and something like prove P of n implies P of n plus 1, n bigger than or equal to 1. And actually write that down as part of your proof, because that will help you, keep straight what it is you're trying to do. And then, start your proof. Step 1, P of n, that's the hypothesis. Step 2, usually this is the definition of P of n. You write it out. Step 3, you do other stuff, right, for various magical reasons. And at some point, P of n plus 1. And whatever reason that was. And then go ahead and state, P of n, therefore P of n implies P of n plus 1, therefore P of n for all n bigger than or equal to 1 because of mathematical induction. And really most induction proofs that I've looked at from people, you have the magic part down, right? Yeah, so all the reasons are magical. Most people were able to find, if I rewrite n factorial as, n times n minus 1 times n minus 2 factorial, then, all this great stuff happens. And that's usually the hardest part. So I think people can do the hardest part. The other essential part, though, is, spelling it out as a formal proof. So just, get some practice going through that. Yeah, because we don't actually accept magic as a valid reason for this class. We do for other classes. Yeah, you need enough mana, and it's got to be the right type. So mathematical induction is basically a land argument, so make sure you have land cards to play. Anyway, no, that's a joke. So this is all final exam comments. Yes, MTG. I miss playing Magic. We used to have a group one summer when I was teaching 270. We'd get together in the lab, and the lab would close at 9, and we'd all stick around and play Magic for a few hours. And that was pretty fun. All right, so study guide is posted on Canvas, and let me just pull that over. And there's a lot in here. If you just looked at this, it would probably be pretty disturbing, because there's a lot of stuff in here. But really, I mean, we've covered a lot of material in here. And again, I think people are really solid on this. So let me just run through here, but keep questions coming, and if there's something you want more information on, we'll talk about it. Haven't played since Revive. So I haven't played since Born of Gods. I don't know how long ago that was, but that was when I kind of lost my circle. Okay, started with set theory, right? And you'll probably see a set theory question on there because, it's easy points, right? So what is a set? It's a collection of things. Operations on set, ways to combine sets. So unions, intersections. Make sure you understand subtraction, right? So let me move this over. So if A and B are sets, we either write A take away B or A minus B, right? This is a set of all things that are contained in A but not contained in B. So we start with A, but we throw away all the stuff that's in B. And when we write A bar or A complement, that's the universal set. with A subtracted from it. So it's everything that's in the universe but not in A. Intersections are the set of all elements such that X is in A and X is in B. And unions are the set of all elements which are in A or in B. And there's the linkage to Engineering 250 Boolean logic, right? Intersections and ands, unions and ors. That's how we tie in, you know, all the stuff that we learn in 250, De Morgan's theorem, adjacency theorem. All of that maps over to set theory, basically because of this. So yeah, ways to combine elements in sets. Definitely good to know. Complements universal set. Examples of sets. So Z is the integers, Q are the rational numbers or fractions, R are the real numbers, C are the complex numbers. We don't usually deal with those. Subsets, power sets. So power set is a collection of all subsets. So the power set is itself a set, and each element in the power set is a set. In particular, it's a subset of whatever set you're taking the power set of. There's always the empty set, right, which is either this or this, right, which is not the same thing as this. This is a set containing one element. This is a set containing no elements. This is a set containing no elements. And we can talk about cardinality of a set. And if that's a finite set, it's the number of elements in the set. If it's not a finite set, we're not going to talk about the cardinality for the final. So don't worry about the weird cardinality stuff. Aleph naught, all of that. Cartesian products, so that's where you basically take ordered pairs. I'm going to have to get the door in a second. So take an element from A and an element from B, put them together in a tuple, right? That's one of the elements in this Cartesian product. So the product is a set of all of those tuples. All right, and set identities, you know, there's basic ones that are pretty self-obvious, like A union A equals A union the empty set equals A union the universal set equals the universal set. Similar ones for complements. And these are good, you know, to think about if you want to brush up on set theory. They help you sort of, you know, re-envision these set operations plus things like the empty set, the universal set, and so on. There's also De Morgan's theorem, and that's definitely a good one to have handy because it lets us go from intersections to unions or vice versa. So, but I'm not going to worry too much about, you know, other set identities. Functions. So functions are maps from one set to another. We can define a function by saying what it maps each element to, and functions go from a domain to a codomain. So if we specify the function value at each point in the domain, that totally specifies the function. So we can also think of it as a set of tuples, right? F and, or, you know, A and F of A. And then there's these, you know, types of functions, characteristics of functions. So injective, surjective, bijective. Injective means different values mapped to different things. Okay, so picture to keep in mind. Different values mapped to different things, that's injective. If you have different values that map to the same thing, that's not injective. So injective means different values always map to different things. Surjective simply means every point is mapped to by something. Not surjective means there's some point that's not mapped to by anything. All right. So injective, different things go to different values. Surjective, every value has something going to it. And then bijective is just both. The other way to think about this is if your function is injective, every point has less than or equal to one thing's mapping to it, less than or equal to one arrow. We could have a point over here that's not mapped to, and it could still be an injective function. But every point is mapped to either 0 or 1 times. Surjective means every point is mapped to at least once. Well, we could have 15 arrows going to this point, it's still surjective. And then injective, every point is mapped to exactly once, because it's both of these. So those, just know the definitions. There might be like, a quick answer question or something like that. Requirements to be well defined, you should know this one. To be well defined, you need to map each value to a particular point. We can't have a point mapping to two different things. That's just not a function, right? So like square root's not actually a function, because what's the square root of 1? Well, it's 1 and it's minus 1. It has two values. That's not really a function. So someone asked, there's no discontinuities. We can't really use the word discontinuity when we're talking about functions unless we have something else. Because these are just, points over here and points over here. So continuity is another thing that has to do with either inverses or some kind of measure of closeness between points. So let's avoid thinking of discontinuities for this. Unless you want to talk about topology, and then it comes back in. All right, so well-defined is simply saying, each point goes to exactly one point. Could be lots of things going to the same point, could be points that don't get mapped to, but each point has to go to exactly one point. That's what it means to be well-defined. That's also the vertical line test in calculus. All right, summations, we talked about summations. It's just a shorthand for, a bunch of things added together. We usually have some variable, some lower limit, some upper limit, and some expression. And this is a for loop. Initialize a running sum to 0, loop from I equals 5 to 10, calculate this expression and add it to your running sum. And there's also, a product notation. And same idea, but it's a running product. Initialize a product to 1 and multiply by this expression as I changes from A to B. And we can do nested versions of these. And the way you do a nested version, calculate the inside sum first, and then just think of this as a plain old summation of whatever expression you got here. Matrices, we just kind of reviewed from 120 or other courses, right? So a matrix is just, a typically two-dimensional collection of values. I won't ask you to do matrix operations. I won't ask you to multiply or add or take the inverse, but you should know a few things about matrices, like multiplication is not commutative. A times B is not always B times A. There's a procedure we have to follow to multiply two matrices together. There's an identity matrix. There's sometimes an inverse to a matrix. But I'm not going to ask you a lot of details on matrices. I will ask you a lot of details on propositional logic, though. So you should know what a proposition is, right? It's a declarative statement with a truth value. And we spend a lot of our time building new propositions from old ones. So, yeah, this will not be a linear algebra final. Sorry if that disappoints anyone. Yeah, I'll have you invert a 20 by 20 matrix using determinants. Know what a proposition is, right? And understand that once we have propositions, we can do things like build new propositions by taking the conjunction or the disjunction of those other propositions. So a conjunction is just an and, a disjunction is an or. So, you know, proposition P is it is sunny, proposition Q is it's Friday. The conjunction would be, you know, it's Friday and it's sunny. And then there's inference. There's this idea of, you know, P implies Q, if P then Q. Right? And we can write truth tables for all of these things. The truth table for if P then Q is a little counterintuitive, at least at first. But you know, it's just another proposition, right? Which happens to be built out of two propositions where we're saying if the first thing, then the second thing. And then there's the rules of inference. So page 58 and 59, I believe, maybe 7 and 8 in your textbook, that list, you know, ways that we can write new propositions from old. So in fact, let me just go ahead and pull that up, rather than waving my hands too much. So page 58, right? So identities about you know, unions and intersections. These are similar to what we encountered in set theory, right? P or false is P, P and true is P, right? P and not P is false, right? And this is similar to, you know, A intersect with the complement of A is the empty set. A union, the complement of A, is the universal set. Well, P ORed with not P is true. Yeah, rock those matrices on a date, definitely. It's a good thing. Why would we invert a matrix by hand using determinants? Well, you have to know how to do that before you can write code to do that, right? That's part of why we learn this stuff. Because at some point, you know, somebody wrote the first computer program to invert a matrix, and they darn well had to know how to do it by hand to be able to tell the computer to do it. And then if you know how to do it by hand, you can look at the computer algorithm and maybe find ways to speed it up. Maybe find some analysis to do on your matrix, and maybe do some arrangement of the rows and columns that suddenly let your inverse operation run a lot quicker. Right? Well, we learn that because we're lazy as humans, and so we don't want to do too much work. But that translates well to a computer program because it doesn't spend as much CPU time, and we get our answers quicker. All right, so these are logical laws. These are common implications and equivalences. I call these rules of inference. But these are things like, you know, given if P then Q and P, we can conclude Q. Given if P then Q and not Q, we can conclude not P. Right? That's the contrapositive, indirect reasoning. So all of these things, right? And you can use your textbook during the exam. You can use your notes during the exam, so you don't need to memorize these. But you want to be familiar with them just from having done proofs, so that when you're trying to prove something follows from a set of hypotheses, you don't have to stare at these, you know, in your second hour of your second final of the day maybe, and hope that something jumps out and says this would be useful. You want experience with it, right? So when you see, you know, a statement about Q and you see a not Q, you think, oh, you know, I can do a contrapositive, or maybe I should do De Morgan's because this says ands and that says ors. So be familiar with them, right? But you don't have to memorize them. Logical equivalence, you know, two things are logically equivalent if they're equally true or false at the same time, right? So if their truth tables are identical, or if they have exactly the same logic value in all cases, they're logically equivalent. Quantifiers are, you know, these things like for all x in the integers, some statement, right, which is typically a proposition involving x. Or there exists, you know, some y in the set of integers such that, you know, some proposition p of y is true. So universal quantifier, existential quantifier. And each of these is a proposition, right? P of x is a proposition. this whole thing is a proposition, which says that this proposition is true for all integers. P of y is a proposition. This whole thing is another proposition which says P of y is true for at least one integer. So we're always building new propositions out of old propositions. That's like, what we do. Fallacies are things that are not true. Right? So theorems are things that are true, which is like, P and Q implies P. Well, that's always true. If this is true and that's true, well, this is true, so this implies P. This is a fallacy. Right? If I know that P or Q is true, P could be false. This might be true because Q is true even though P is false. So that's a fallacy. But this, yeah, and P and Q also implies Q. Good. All right, so proofs. You'll definitely be doing a couple of proofs. Okay, there'll be a general logic proof. There'll be a mathematical induction proof. So the general logic proof is, like those homework questions that we've done. Where'd my textbook go? So take a look at chapter 3, section 5 for an idea of these proofs. So look at these examples, right? Direct proofs, indirect proofs. So you'll definitely see a question that looks something like this, right? Where I give you a set of hypotheses and I ask you to prove a conclusion. For example, given this and this, prove not A. So you'll see something like that, and it's really just, kind of down to the metal propositional logic. And you did a bunch of exercises from here, so I suggest going through those as practice. There's solved problems. The even numbers have solutions in the back. So, modulo typos that we occasionally find. You can check your work and see if you're doing the right thing. But usually, if it feels like you're kind of doing something slippery, you may not be doing a totally valid proof. If you do a valid proof, usually right? Once you've gotten good at this, you can feel, like, yeah, this is rock solid. This would stand up in a court of law. So go through there and look at examples. All right. Proofs about even and odd numbers. Proofs about divisibility, right? The basic strategy is start with what you know and argue logically to what you're trying to show. But watch out for the pitfalls. Don't accidentally write down what you're trying to show and then start building on that. Okay, that makes an invalid proof. Make sure you're trying to prove the right thing, right? If a number is even, its square is even. Make sure you're proving that if a number is even, its square is even. Not that if a square is even, the number is even, right? So make sure you're doing the right direction for your proof, and then just start with what you know. In that case, a number is even, right? And then write it as 2 times an integer, because that's what it means to be even, and work logically, apply logic, apply algebra, and so on until you get to something which proves that, the square of that number is even, or whatever it is you're trying to show. The only time you can start with what you don't know is when you're doing an indirect proof. So if we're doing a proof by contradiction, we might start off with a particular statement and then argue until we get a contradiction, at which point we can say that original statement must be false. And so the way we do this is typically we're trying to prove P implies Q. Well, we're going to assume P because that's the hypothesis. But we'll assume not Q. That's the negation of the conclusion. We don't know that this is true. We're just assuming it. But we're going to go on, and eventually we're going to prove that false is true. And that's our contradiction. And once we reach that, we realize that this statement must be false, which means the negation of that statement must be true, which means Q must be true. Cool. Someone commented they were intimidated by proofs before the class, but now they enjoy them. That's awesome. I think proofs is one of like the big takeaways from this course, right? That and mathematical induction and how it ties into recursion. But proofs are so essential, right? For you know, being a programmer, for knowing if your algorithm is going to be correct. And you know, when you're writing code, you're putting down some Java or whatever, right? You're not thinking about, you know, logical syllogism, you know, or indirect reasoning or something like that. But the processing that's going on in your brain to know that what you're doing is correct is basically the same thing. And the more you can kind of ingrain, you know, some of the steps that you have in constructing a proof in your head, the more efficient you're going to be when you're trying to come up with an algorithm to solve, you know, whatever kind of problem. So that's all good stuff. Cool. Yeah, it is fun when the stuff builds and the scary stuff becomes interesting. That's definitely part of the fun of learning, you know, stuff. Cool. All right. So we'll talk about induction in a few minutes. Number theory. So basic concepts here, right? So know about divisibility, the definition of it, and remember there's this funny notation, right? A vertical bar B means A divides B, which means B over A is an integer, which means B equals some integer times A, right? And if you mistakenly think of this as being this, then you know you're completely backwards and things get strange really quickly. So this is just a notation we use to mean A divides B. B is divisible by A. B is a multiple of A. A is a factor of B, etc. Finding congruence. So congruence is basically just looking at remainders, right? So we have two numbers. We take one and divide it by the other. We can ask what's left over after we do that integer division. Whatever's left over, that's what that number is congruent to, that first number modulo the second. So, you know, I always pick on 23 and 3. 23 divided by 3 equals 7 with a remainder of 2. Okay, we don't really care about the 7 part, we only care about the remainder. So I would say 23 is congruent to 2 modulo 3. Right? That's really all that stuff comes down to. But we can wrap it in formalism and flowery language and make it sound much more intimidating. But really, it's just, you know, do division, take remainders. All right. So modular arithmetic. The nice thing about working with remainders is we can do arithmetic on remainders, or we can do arithmetic on big, long, complex numbers, and then take remainders at the end. It's the same thing. 23 is congruent to 2 modulo 3. I'm guaranteed that 23 squared is congruent to 2 squared modulo 3. 2 squared is 4, which is congruent to 1. So without doing any big complex math, I know if I take 23 and square it, it's 1 more than a multiple of 3. Okay, that's the whole power of modular arithmetic. Because I can work with these tiny little numbers over here and make statements about really big numbers over there. Right? I know that 23 to the 8th is going to be 1 more than a multiple of 3. I did it in my head. Why? Because 23 to the 8th is this to the 4th, and 1 to the 4th is 1. Cool. All right. What else? Uniqueness of modular equivalence. So this is something called the division algorithm. You should know what I mean when I say the division algorithm. The division algorithm is really just a theorem. And it basically says, you know, 23 is 2 more than a multiple of 3. 23 is also 5 more than a multiple of 3. 23 is also 8 more than a multiple of 3. 23 is actually a whole bunch of things more than a multiple of 3. It's actually 1 less than a multiple of 3. All of these things are true. But when we're dealing with equivalences, sometimes it's nice to choose exactly one of these, right? And the one that we want to choose is some value which is bigger than or equal to 0 and less than, in this case, 3. And there's only one thing 23 is congruent to that's bigger than or equal to 0 and less than 3, and that's this right here. And so the division algorithm basically says, you know, given some number a and given some modulo m that we're working, we can always find some b that a is congruent to with a property b is bigger than or equal to 0 and less than m. That exists and it's unique. That's the division algorithm. And so I may ask you to find, you know, what 23 is congruent to modulo 2, and I may specify it has to be, you know, between this range of values. Division theorem says, you know, you'll always be able to do that, and your answer will be unique. So that's division algorithm. Primes, you should know what a prime is, right? It's a number bigger than or equal to 2 that has no factors other than itself and 1. So 2, 3, 5, 7, 11, 13, 17, and so on are all prime numbers. Fundamental theorem of arithmetic. Make sure you know this. If it's called the fundamental theorem of something, it's worth knowing. Fundamental theorem of arithmetic is about factoring numbers into products of primes. So if I take a number like 50, I can write it as 2 times 5 squared. And that is a unique way to write 50 as a product of primes, other than, you know, doing goofy things like 5 squared times 2 or 5 times 2 times 5, right? Those are technically different ways to write this, but it's the same set of factors and the same powers. So fundamental theorem says that this is unique. If you have a prime number, it's just, you know, a prime number. And that's a really useful theorem. We don't use it a whole lot, but it does kick in other parts of mathematics. Number of primes, you should know there's an infinite number of primes. Greatest common divisor is the largest positive integer that divides two numbers. We're only going to deal with positive numbers here. And there's a thing called the Euclidean algorithm for finding the GCD. We did this on homeworks. You'll probably do this on Monday. So, you know, find the GCD of, I don't know, 50 and 12. So, right, 50 is, you know, something times 12 plus some remainder. And then carry these things over. 12 is 6 times 2 plus 0. Once you get a 0, this is your GCD. So that's the Euclidean algorithm. So make sure you're okay with applying that. Modular operations, modular exponentiation, and Fermat's little theorem are the two I'd like you to know. So modular exponentiation, we did homeworks on that, right? If you want to find, you know, a to the b modulo c, we find a to the 1, a to the 2, a to the 4, a to the 8, a to the 16, and so on, all mod c. And we find each of these by simply squaring the thing that we just found before that. When we want to find a to the 16th, it's congruent to a to the 8th squared. And once you know a to each of these powers, which is a power of 2, then we can find a to the b by writing b as, you know, 16 plus 4 plus 1. And it would be congruent to a to the 16th times a to the 4th times a to the 1st. So brush off the neurons on that and put that on your bag of tricks. And then Fermat's little theorem was, you know, a to the p minus 1 is congruent to 1 modulo p. Except in the case where a is a multiple of p, in which case this is congruent to 0. And this works for doing large operations, because if we know a to the p minus 1 is congruent to 1, we know that a to the p minus 1 squared or cubed or raised to the millionth is still congruent to 1. So if we can find a multiple of p minus 1 that's close to b, we can, you know, do most of our multiplications and know that our power of A is still congruent to 1. And then we just kind of ootsy it up the last few steps to get to B. So there was a homework set on all of that. And while we're in here, I forgot to mention this in the 224 classes, but people should know this anyway. But just a quick reminder, on the Canvas page, there's this video timestamp index, right? If you click through on that, there's a list of all the topics that we've talked about in this course, as well as 224 or 223. So, you know, if you want to find modular stuff, just search for modular. Examples of modular arithmetic. So it's that lecture, and it was at, you know, 56 minutes 49 seconds into the lecture, and so on. So you can, you know, modular arithmetic, modular exponentiation, right? So use that as to help with your studies. Do we use modular exponentiation for Fermat's Little theorem? No, they're really two different terms for achieving the same kind of outcome. But Fermat's Little theorem is something like this. You know, find 10 to the 112th modulo 11. Right? So modular exponentiation, we'd find 10 to the 1st, 2nd, 4th, 8th, 16th, 32nd, and 64th. And then we'd multiply some of those to get 10 to the 112th. Fermat's Little theorem tells us that 10 to the 10th is congruent to 1 modulo 11. Let's say I want to do 102. So it tells us this thing raised to the p minus 1 is congruent to 1 modulo p. So if 10 squared is congruent to 1, 10 squared to the 10th, sorry, 10 to the 10th to the 10th, which is 10 to the 100th, is congruent to 1 to the 10th, which is still congruent to 1 modulo 11. So Fermat's Little theorem lets us jump to something like this. And then, since we're trying to find 10 to the 102, I have to do two multiplications. So 10 to the 101 is congruent to 10. 10 to the 102 is congruent to 100, which is congruent to, well, it's still congruent to 1, because 9 times 11 is 99. So that's Fermat's Little theorem. All right, oh, we got plenty of time. Let's see. Applications of number theory. So, and applications of all of this modular exponentiation. We talked about parity, even parity, odd parity, right? That's just modular too. But in general, we can do modular operations for things like check digits, ISBN codes, universal pricing codes. I'm not going to ask you any details on that, right? Just be aware that those are the kinds of things that we can do with these number theoretic concepts. So working, you know, modulo something, we can compute a check digit. If you have a Visa number, we can look at the 16 digits and figure out if it really is a valid Visa number or not. And it's, you know, doing modular arithmetic on the digits. Let's see, cryptography. So what do I want to know about cryptography? You should know what a cipher is, right? It's a way to change plain text into jumbled up text that's not, you know, directly readable. We talked about two particular ciphers, a Caesar cipher, which is just, you know, replace these letters with those letters. So sometimes called a shift cipher. This is the decoder ring. So let's replace A with E and B with F and C with G and so on. A shift cipher is, sorry, I meant to say translation cipher. Well, a Caesar cipher is a shift cipher. We also had a transposition cipher, which was, you know, A, B, C, D, E, F. well, maybe our cipher is, we break this into groups of 3 and we just reverse the order of these. So this would be C, B, A, F, E, D. And main thing to know is that these are not terribly secure, right? We can attack them by using properties of words and whatever language we have. We can look for patterns, things like that. I'm not going to ask you to, encrypt something or decrypt something. Again, high order conceptual questions, possibly. Symmetric versus asymmetric or public key ciphers. All I want you to know here is that there is such a thing as an asymmetric cipher. And the symmetry refers to the following aspect of an encryption system. If you know how to encrypt, do you also know how to decrypt? If you know the password for coding something, does that give you the password for decoding? And traditional ciphers, shift ciphers, things like that, if you know how to do the encryption, you know how to do the decryption. If you know you're adding 3 to each letter to encrypt, all you got to do is subtract 3 to decrypt. Those are symmetric ciphers. And that's what most of the world used until, the 70s. An asymmetric cipher is one where you have one key for encrypting and a different key for decrypting, and you can't get one from the other. So I can tell people how to send me an encrypted message, and they can't decrypt the messages that are being sent. Because the decryption key is totally different. Okay, so that's what's also called a public key cipher. The public key is the encryption one that people use to send me stuff, but the private key is the one that I use to decrypt. And so if I'm doing e-commerce, I can tell people, code up your credit card using this encryption key, and everybody can do that, and nobody can read these encrypted messages, even though they know how to encrypt them themselves. Only I can decipher them because I have the decryption key. Right? Won't ask you to prove it, do anything with it, etc. Just know what that difference is. But there is a video on YouTube that I posted a while back when we were doing this that actually goes through the process of using a public key encryption system to code a message using RSA. So if you're curious about that and you haven't checked it out, check it out. All right, on to induction. Induction is your friend. So, we touched on this a little bit in the beginning of class, this idea that to do an inductive proof, you're basically, trying to prove some proposition is true for some set of values. So start off with let P of n be the proposition. And then state what the proposition is. So if you're asked to prove, that all pigeons are gray, let P of n be the proposition that any set of n pigeons are all gray, right? And to prove that all pigeons are gray, you would want to prove P of n for n bigger than or equal to 1. I won't ask you about pigeons or cows. But, so start off with a proposition. It's going to be a family of propositions, and you're trying to prove, typically P of n for all n, usually bigger than or equal to 1 or bigger than or equal to 0. Could be bigger than or equal to 1,000,000. Could be for all even n bigger than or equal to 6. But, you're trying to prove that some family of propositions is true. And we do it in 2 steps. The base case, which says, prove that P of some initial value is true. So state, base case and prove P of 6, and then write out what P of 6 is and explain why it's true. And then the inductive step, which is the bigger part of the work, which is proving P of n implies usually P of n plus 1, where n is, whatever values of n we're interested in. And to prove this, all we have to do is assume P of n is true and show that P of n plus 1 follows. Right? Now we're not proving that P of n is true. We're not proving that P of n plus 1 is true for all n. We're proving one very, very narrow thing, which is if we assume P of n is true, we can prove P of n plus 1 is true. So make sure that's exactly what you're trying to prove. start off with the hypothesis P of n, usually go ahead and write out what that means, right? So plug in the definition of P of n, and then, you know, do your work, algebraic manipulation or, you know, logical reasoning or something until you get to P of n plus 1. At that point, you've shown that starting with P of n, we can show P of n plus 1 is true. Go ahead and write that down. P of n implies P of n plus 1. Therefore, now swing the mathematical induction wand at all of this and say P of n is true for all n bigger than or equal to 1 because of mathematical induction. And you're done. And I'll probably give you an inductive question that you know, uses some algebraic manipulation, so something about an equation, as opposed to, you know, something about placing tiles or using postage stamps or something like that. So it'll be a fairly straightforward induction question, hopefully. Recursive functions, we didn't do a whole lot with these, so probably not a whole lot to say about that. But, you know, a recursive function was a function written in terms of smaller values of the function. So our sort of classic example is, you know, f of n equals f of n minus 1 plus f of n minus 2, where n is bigger than or equal to 2. That's how we define a Fibonacci series. And we also define f of 1 equals f of 0 equals 1. So base cases. Right, so that's a classic recursive function. But we can start to think of other functions recursively. For example, to write down the sum of the first n integers, right? We could say Sn equals n plus the sum of the first n minus 1 integers, where n is bigger than or equal to 1, and we could say the sum of the first 0 integers is 0. So there's a recursive function for writing sums of integers. We know that n squared is the sum of the first n odd integers, so we could write a recursive function for a square. That would define, you know, x squared in terms of x minus 1 squared. Right? And it's really, you know, we're grabbing onto some pieces of mathematics here, right? This is a bit of a sidebar, but it's too fun not to do. Right, we know x minus 1 squared is x squared minus 2x plus 1. So if I take x minus 1 squared and I add 2x and I subtract 1, what do I get? I get x squared. Well, you know, I can define a function now, q of x is equal to q of x minus 1 plus 2x minus 1 when x is bigger than or equal to 1, and I can say q of 0 is equal to 0. There's a function that gives you the square of a number. And it's a recursive function. There's no looping in here per se. It's not like you know, doing a for loop where you add things, but I can define this function in terms of the function itself. And then I could write that recursively in C if I wanted, and I can prove that this works by using mathematical induction. So all this stuff kind of ties together, and if it feels kind of like jumbly right now, that's probably good. That's probably a good sign. All right, so recursive functions, pigeonhole principle. So this is about counting. So this is all stuff that's post the midterm, right? So counting was this idea that if you have n containers and n plus 1 objects, you're going to have at least one container with at least two things in it. So you're putting things into containers. If you only have n objects and you have n containers, you could put them in the containers so each container has only one thing. But if you have an n plus first object, something's going to get doubled up, right? And you could put all your things into one container, that's okay. Pigeonhole principle says, you know, at least one container has at least two things. All right, and there's a generalized version of that where you have, you know, n objects and k containers, but the same idea. And we can use this to answer, you know, basic counting questions like how many people can be in a room, and still have, you know, unique days of the week that they were born on. Well, if there's 7 people, they could each be born on one of the 7 days. Pigeonhole principle tells us if there's 8 people in a room, at least 2 of them have the same birthday of the week. All right, moving on with counting, we talked about the product rule and the sum rule. So product rule is a way we can enumerate the number of ways to do some task as a product of the number of ways to do different steps that make up that task. So we have some task T, and we can do it as a succession of T1 followed by T2 followed by T3. Well, if we can do this n1 ways and that's n2 ways and this n3 ways, then we can do n a total of n1 times n2 times n3 ways. This is where these are done in succession, though. If we can do a task by doing either T1 or T2 or T3, and this can be done n1, n2, and n3 ways, then the number of ways we can do T is the sum n1 plus n2 plus n3. So if you have to do all 3 of these tasks, do T1 and then do T2 and then do T3, it's a product rule. If you can do T by doing T1 or T2 or T3, it's a sum rule. And this is again another revisitation of this idea that OR goes with sums and ANDs goes with products. Right? That's going to keep coming up again and again in life, but especially in computer science and engineering life. All right, so that's product rule, sum rule, and we can do combinations of those, and we can also do this principle of inclusion-exclusion, which is this idea of number of things in A union B is number of things in A plus the number of things in B minus the things in the intersection. And that comes into various counting arguments. I will not ask you about this with more than 2 sets, though, because it's a really weird rule when you have like 3 sets like this. All right, from the idea of product rule and sum rule, we can come up with a general notion of permutations and combinations. Okay, permutations are ordered, combinations are unordered. You got to get those right, okay, because they fundamentally change your answer. So permutations depend on the order. So think of the permutation lock on your locker in high school. And trying to convince your friends it's really a permutation lock. So permutation, n objects, and you want to take r objects out of that, right? It's n factorial over n minus r factorial. But you can get this directly from the product rule. It's just a shorthand notation. If you're picking r objects out of n, there's n ways you can choose the first object, n minus 1 ways to choose the second, n minus 2 ways to choose the third, and if you multiply all those out, you get n times n minus 1 times n minus 2 down to some point. That's what this is, right? This is all of your numbers up to n multiplied, and when you divide out those smaller ones, you get just, you know, n times n minus 1 times n minus 2, for example. All right, so that comes straight out of the product rule. That's when we care about the ordering. If we don't care about the ordering, then we have a combination. So this is ordered. This is unordered. And to find the number of unordered ways we can choose r things from n, we just take the number of ordered ways and divide by the number of ways we can order those r elements. And how do we know that there's r factorial ways to arrange this? It's another product rule. Right? If you have r elements, you have to choose which element comes first, which comes second, which comes third, and so on. And the number of ways to do that is r minus 1, r minus 2, and so on. So the number of unordered arrangements is the number of ordered divided by r factorial, which means we can write our cool little formula with a third exclamation mark, like that. And there's a shorthand for this, which is n choose r. And if you see n and r in parentheses like that, that's not n divided by r, it's n choose r. You probably won't see that on the exam because it's going to be in Canvas, and I don't want to try to write that up in Canvas. So I usually do this. All right, that's permutations and combinations. Pascal's triangle, just know that it's really cool. I won't ask you specific questions about it. But, you know, if someone asks you, just say, yeah, it's cool. Binomial theorem is this fact that if you want to do a plus b to the n, these coefficients come out of the nth row of Pascal's triangle. So I want you to know that, right? And yeah, if I ask you, is Pascal's triangle cool, you have to say true, because that's the right answer. All right, so then we're up to the last few weeks of the course, which was graph theory and grammars and languages. So graph theory, we talked about a lot of stuff. What do I expect you to be able to do on the exam? A subset of those things. So I want you to know what a graph is. I want you to know about, you know, plain old graphs where we just have dots connected with lines, but also directed graphs where we have an arrow on each edge, right? So we have a notion of going from one vertex to another. And you should know about weighted graphs where we have, you know, some value associated with each edge. You should know what vertices and edges are, right? Vertices are the dots, edges are the lines or arrows connecting the dots. It's that simple. The degree of a vertex is the number of edges going into it. If we have a directed graph, we have two degrees, an in degree, which is the number of edges going in, and an out degree, which is the number of edges going out. Right, so you just add those up, and you can find the sum of the in degrees and the out degrees. The one trick here, if you have a loop, that edge that, you know, starts and ends back here, that contributes 2 to the sum if we're adding up, you know, the degrees of a vertex. So a graph like this would have a degree of 2. Now that vertex has a degree of 4. Right, because you count both that and that. And that just makes things work well. So degrees of vertices, you should be able to find the degree of a vertex. A path is you know, start at a vertex and just follow from vertex to vertex. There's ambiguity out there as to, you know, simple paths and things like that. So here's what I want you to know. Right? If I start here and I just follow from edge to edge, that's a path. If I come back here, it's still a path. If I come back here and come back here and come back here and come over here, that's still a path. Okay? What is not a path is if I start here and I go here and then I were to jump to this vertex. Right? It's no longer a path. So really, when we talk about a path, all we're talking about is a series of edges where, you know, one edge ends where the next edge begins. All right, and a cycle or a loop is a path where the last vertex is the same as the first vertex. So we come back to where we started. So technically, you know, if I start at A and I go to B and I come back to A, that's a cycle, right? All right. The other thing I want you to know is an Euler path and a Hamilton path. So Euler paths. You travel along each edge exactly once. Okay? You have to travel on each edge, and you're only allowed to do so once. A Hamilton path, you have to visit each vertex exactly once. If you have to draw graphs, yeah, unless I ask you to do ASCII art graphs, which would be really cruel and unusual, so I won't do that. Yeah, I'm probably not going to have you draw graphs, but you can expect to see graphs and answer questions about them. Otherwise, yeah, I would have to give you an extra hour. All right, so Euler Path, each edge is traveled exactly once. Hamilton Path, each vertex is visited exactly once. Okay, and those are the only nuances of paths that I'm going to ask you about. So I won't ask you about simple or things like that. That would be cool, writing a program to draw the graph. That's actually pretty challenging to do with ASCII art, but it's a fun exercise. All right, representations of graphs. So three main ways we've talked about to represent a graph. Adjacency lists, adjacency matrices, and incidence matrices. And chances are I'm going to ask you about adjacency matrices. But, you know, basically, if you have a graph, you know, A, B, C, D, what's an adjacency list? Well, A, we list all the edges, all the vertices that are adjacent to it, connected by an edge. B, we do the same thing. C, we do the same thing. D, we do the same thing. That's an adjacency list representation. All right, an adjacency matrix we write, you know, typically a 1 or a 0 or a true or a false everywhere that there's an edge. So A is not connected to A, but it's connected to B and C and not to D. B is connected to A and C. C is connected to A, B, and D is connected to only C. There's an adjacency matrix. An incidence matrix, you know, we have to label the edges, E1, E2, E3, E4, and then we would have a matrix with vertices on one side and edges on the other, and we would indicate whether each edge was incident with a vertex. So E1 is incident to A and B, E3 is incident to B and C, E2, A and C, and so on. And this is by far the most common, and so you can probably expect that I'll ask you to either draw an adjacency matrix for a graph, or, you know, look at a graph defined by an adjacency matrix and answer some questions. So you know, I won't ask you to draw a graph and submit it, but, you know, I could say something like, you know, which vertex has the greatest degree, or, you know, what's the degree of each vertex in this graph, and you would have to draw this graph on paper to be able to answer those questions, right? So that kind of thing is possible. All right, what else on graphs? Isomorphisms of graphs. So what is an isomorphism between two graphs? It's a one-to-one mapping from the vertices of one graph to the vertices of another that respects this idea of edges, right? So if two graphs are isomorphic, we should be able to map the vertices of one to the vertices of the other and preserve the notion of an edge. So these two vertices are connected by an edge if and only if the things we map them to are also connected by an edge. Right? So that's the formal notion of two graphs being isomorphic. All right, and I will not ask you Dijkstra's algorithm. So if you were going to study it, hopefully you've already studied it, but I'm not going to put a Dijkstra's question on there, because that's just too jumbled up on an online quiz. So tuck Dijkstra away, because you'll use it in other courses for sure. All right, so languages and grammars. So basic idea of a phrase structure, grammar, right? That four tuple of symbols, terminal symbols, start symbol, and production rules. And I'd like you to be able to either write a phrase structure grammar to describe a certain language, or look at a phrase structure grammar and tell me some things that are recognized, some things that belong to that language. So it could be going in either direction. So analysis and synthesis. Finite state machines, you know about finite state machines from 250, and you know, from programming and other stuff. So basic concepts there. State diagrams, I probably won't ask you to draw a state diagram, but I could show you a picture of a state diagram and ask you, you know, what's a string that's recognized by this machine, or you know, some question like that. So recognizing strings with state machines. Turing machines, you know, we know the basic concept of it, right? So current state, current symbol, new state, and move left or right. And, you know, I probably won't ask you to come up with a Turing machine program on the exam, but I could give you a program and show you the initial contents of a tape and ask you, you know, what does the tape look like after this program runs? Or more likely, you know, I would ask you first, you know, show me the first 5 operations this machine would do given this tape and this program. And I'd ask you to show me what state you go into, how the tape gets modified, and play it out like that. All right, and there you go. There's 2:15. You could have skipped the whole quarter and just come to this hour and 23 minutes, and you would have had the whole thing. Hour and 13. No. So this is a lot of material, right? And a lot of it is, you know, first exposure. It's stuff that will either, you know, come up again and again down the road. You know, you'll do a whole course on automata theory at WSU, or stuff that, you know, sort of works into this kind of mental soup that comes to bear when we, you know, are working on programming or trying to figure out a bug or something like that. So pretty much whatever you take away from this is you know, bonus. You know, I'll test you on some set of these things along the lines of the homework questions. But you know, the stuff that's really important you're going to encounter again and again, and it's going to sink in further each time. It's like KVL, KCL, right? So you encounter that in 120. If you're a double E student, you encounter it in later courses. You'll encounter it in your physics courses when you get to electricity and magnetism, right? And the more time you've had for it to sink in, the better your chance of coming at it with a better understanding. So that's what a lot of this stuff is. So don't worry too much, you know, if it's like, I really don't get mathematical induction. I can do the steps, but I don't really understand it. That's fine, right? Do the steps so you can get, you know, maximal credit on your test. But it will, you know, kick in over time. All right, so I will let you out 4 minutes early unless there's any questions, but I want to, you know, as I said in my other classes, I really want to thank you for all your work and effort and attention in this course. I think it's a really fun course, but it's definitely, you know, got a lot of material in it and a lot of work to do. So, you know, hopefully have a good rest of the day, great weekend. I will probably see you, well, if you're in 224A, I'll see you Monday morning, but I'll see you 12 o'clock on Monday for the exam, and it's from 12 o'clock to 1:50, not 12:30. Don't rip yourself off. 12 o'clock to 1:50 Monday. All right, cool, thank you. Have a great one, and I will see you Monday.